So because running a bunch of different t-tests is not the option here, but we do have a significant ANOVA result, what we need to do is run what's called a post hoc test. Post hoc. The specific variety that we're going to run, there's a bunch of different ones, but we're going to run a pairwise t-test, or really a series of pairwise t-tests, with what's called a Bonferroni correction. A technical term, but you don't really need to know all of the details of what's going on here. Just know that the Bonferroni correction is one of the ways that you can correct those p-values, so that they're actually reflecting the fact that you are committing kind of an error in doing multiple comparisons, that you're running a bunch of statistical tests on the same data, trying to find different things that predict the same y-axis variable, the same response variable. The function that we're going to use is pairwise.t.test. This function will take our data, BARM data, and the Easting coordinates, which is what we're interested in. It will take the label from that same data set. And so this is kind of similar to the model that we specified above, our ANOVA, our linear model. It's Easting, it's our label, but we also need to specify that the adjustment method that we're using on our p-value, using the p.adjust.method argument, is the Bonferroni. If you inspect the pairwise t-test help page, you'll find these arguments listed and your different options for p-adjust methods. And so if we run this, what we're doing is basically what I said was the problem, running a bunch of t-tests comparing the different kind of options of the different pairings for these three different artifact types. But we're not doing it indiscriminately. We're doing it using a Bonferroni correction to account for this multiple comparisons issue. If you run this, you'll see that what we get is a nice little table here. We've got flake axes, we've got denticulated and notched pieces, and then we've got microburins and flake axes. And so if you look, flake axes and microburins, we've got a p-value here of 0.383. If you look then at denticulated / notched pieces and microburins, p-value is 1, very high. They're pretty much the same, it seems. If you look at flake axes and flake axes, we've just got a hyphen here, just the dash, because you're not comparing them to each other. They're the same. And if you look denticulated notched pieces and flake axes, here we have a p-value of 0.031. That is a significant p-value, right? And it's not actually 0.031. It's a corrected, Bonferroni corrected p-value. So in reality, it would be quite small. But this is the p-value. We can report all of these kind of in a table format, saying that it looks like flake axes and microburins and denticulated notched pieces and microburins, they're not significantly different from each other. The Easting values are not significantly different. What's driving our significant ANOVA result is really just the fact that denticulated and notched pieces are significantly different in their Easting coordinates from flake axes. These two types of artifacts are significantly different from each other. Right? Microburins overlap with both to an appreciable degree that the p-values are not significant. It's just the flake axes and the DN pieces. That's what's driving our significant ANOVA result from previously. And so reporting then the results of this pairwise t-test with a Bonferroni correction, this post hoc test, which is what it's called overall, this is kind of the next step. Now, this is only something you do if you get a significant p-value in your ANOVA. If your ANOVA is not significant, there's no point to doing a pairwise t-test or any kind of post hoc test, because the ANOVA is what's identifying whether those different categories have an effect on the Easting coordinates in this case. And if there's no significant result from the ANOVA, there's no reason to do a post hoc test. This is simply what you do when your ANOVA is significant, when your linear model is significant, and you want to inspect then which exact pair of artifact types, which exact pairing of groups is responsible for that significant p-value, what's driving it. In some cases, it will be significant p-values across the board. All of these might be significant p-values. In some cases, just a few, and in this case, just one. And so this is what you do when you're running a linear model on a predictor variable that takes the form of a bunch of different groups or categories. It could be 3, it could be 10, it could be 20. That doesn't matter. But then if you get a significant p-value there, you have to remember that you can't just run a bunch of t-tests or other linear models indiscriminately because of this multiple comparisons problem. The more tests you run on the same data set, the more likely you are to find a false positive. The more likely you are to find a green jelly bean, so to speak. And that would be a spurious conclusion if you were to say that that was a real effect. That's just potentially a random effect. It might be real, it might not be. But you can't say because your p-values at that point will be meaningless. You need to correct your p-values with some method, of which Bonferroni is just one. There are others out there. So this pairwise t-test process with a Bonferroni corrected p-value, that's one way to run a post hoc test on a significant linear model in this case.